Swayam Prabha. Digital India. Educated India.
In the previous classes, we have been looking at how to calculate the response of an RC circuit to a unit step. Now, this method is applicable to any system described by a first order differential equation and excited by a step input. Okay. So, I think we have a good handle on this. Today, we will look at one particular case which needs extra care if we have to get the step response correctly. We said that the step response in an RC circuit and exactly the same thing will hold in an RL circuit as well. In a first order RC RL circuit, what we need to know are, let us say we are calculating a particular quantity Vx. We could be calculating anything, okay. We could be calculating some voltage or some current, it does not matter. So, we need to know value of Vx at t equals 0 plus, that is just after the step is applied, value of Vx at t equals infinity, that is when the circuit reaches steady state, and the time constant tau. Now, once you have all of this, okay, the response is given by okay. So, this is a general expression that is applicable to any quantity in a first order RC or RL circuits. In our examples, we have been taking only an RC case, that is with a capacitor, but the same thing applies to an inductor. If we have time, we will work out an example today. Now, how do we find the value of Vx at t equal to 0 plus? We do that by shorting all capacitors. We can short circuit all capacitors, or if the capacitors have initial conditions, what we really do is replace capacitors by voltage sources whose value equals the initial condition. Okay. And how do you find at t equal to infinity? You simply open circuit all capacitors, because if the voltage reaches a steady state, a constant value across all capacitors, then their currents will be 0. By the way, we are talking only about first order systems here, but this is the case for all RC or RL circuits. And in case of inductors, we have to short circuit all inductors. Okay. And also it turns out, just like you replace capacitors by voltage sources that represents the initial condition, for t equal to 0 plus, you have to replace inductors by current sources. Okay. And finally, how do you find the time constant tau? You find the Thevenin equivalent resistance across the capacitor. Okay. So, this is the algorithm. Now, are there any questions about this? Any questions about these steps, how to follow them, how they come about? Okay, so if not, let me go to a slightly more complicated example than what we looked at in the previous lecture. So, again this is Vs and it goes from 0 to jumps from 0 to Vp, okay, and I will have R, C, and let me call this C1. Okay. So, Vs jumps from 0 to Vp, and let us say I am interested in this voltage Vc, the voltage across the capacitor C. Okay. So, what I would like to know is how to go about finding this. Okay. As usual, I need to find out Vc of 0 plus, that is just after the step is applied, Vc of infinity, that is after an infinitely long time, and the time constant tau. Okay. We have to find all these three, but first let us start with Vc of 0 plus. So, I would like the participants to give me an answer. What is the value of Vc just after the step is applied, that is Vc of 0 plus? What is the value? The input Vs jumps from 0 to Vp. What do you think is the value? There is an answer that says it is Vc of 0, the initial condition on the capacitor. Now, let us say the initial condition on the capacitor is 0 volts. Okay. Then what would be the answer? Let us say that this is initially discharged. So, now clearly the contradiction is obvious. Now, the problem is that there is a loop of voltage source and these two capacitors. Okay. Now, so far we were considering that the voltage across a capacitor will not change instantaneously. We know that that is the case if the current through the capacitor is finite. Okay. Now, if you consider just at just after the step is applied, so this voltage here, which is the sum of voltages across C1 and C, that changes from 0 to Vp. Okay. So, when it changes from 0 to Vp, if we say that the voltage across capacitor C does not change, the voltage across capacitor C1 has to change. Alternatively, if we say that the voltage across C1 does not change, then the voltage across C has to change. Okay. That is, we have this loop of capacitor, two capacitors and a voltage source. If the voltage source changes its value, the voltage across at least one of the capacitors has to change instantaneously. Okay. So, this is the problem. At least one capacitor has to change its voltage instantaneously. Okay. Now, it cannot be just one which changes, because if the voltage across C1 changes instantaneously, that means that there is infinite current flowing through it. But then we assume that capacitor C did not change instantaneously. Okay. So then KCL at this node will be violated, because you have finite currents through C and R, but infinite current through C1. Okay. So it cannot be that only one changes. In fact, both the capacitors have to change their voltages instantaneously. Okay. So while logically at least one have to change, it cannot be only one. In fact, the answer is that both C and C1 have to change their voltages instantaneously. Okay. So now that means that if they are changing instantaneously, infinite currents are flowing through both C1 and C. Okay. Now, because infinite currents are flowing through them, whereas a finite current is flowing through R, because the voltage across that is still finite, okay, we can approximate the circuit without any loss of accuracy by removing the R altogether. Okay. Because the current through this is infinity, this is some finite value. If you add that to the infinite current, it does not change anything. So we can approximately find the answer by removing the resistor altogether and having only C1 and C. Okay. Because just as the step is applied, the current through this loop is infinite, and this resistor contributes only a finite current. So there is no loss of accuracy if you just remove the resistor. Is this clear? So then, assuming that both of them change, we have to calculate the change in Vc. Okay. So let us assume again that C is initially discharged. Okay. C is initially discharged, that is at t equal to 0 minus, we have 0 volts across this, which also means that there is 0 volts across C1. Okay. Because before t equal to 0, Vs is 0, the voltage across C is 0, and voltage across C1 is 0. So what I would like you to find out is the voltage Vc, that is the voltage across capacitor C, when a unit step Vp is applied. Okay. There is an answer saying it is Vp, but it cannot be Vp, because if this changes by Vp, it means that the voltage across C1 does not change at all. Okay. That says that if there is no change in voltage across C1, there will be no current here, but the voltage across C has changed abruptly, so there is infinite current there. Okay. So KCL will be violated at this node. So it cannot be that only one of them changes. Both of them have to change, and they have to change by an appropriate amount, so that KCL here is also satisfied. Okay. So, now because the currents are infinite, we cannot do useful calculation with currents. So, we will work with charges, which are integral of currents, time integral of currents. Okay. So, now if you consider this as a node, what KCL says is this current I1 has to be equal to this current I2. Okay. Now, of course, when capacitor voltages change abruptly, these currents will both be infinite and we will not be able to do useful calculations with that. Okay. So, this is C1, this is C2 and this is Vs, which changes from 0 to Vp. Now, the same KCL can be rewritten by saying that instead of currents, I will say the amount of charge that flows that way, Q1, has to be equal to the amount of charge that flows this way, which is Q2. Okay. Is this fine? So, now let us consider the circuit for t equals 0 minus, that is before the step appears. So, we have 0 volts here and 0 volts there and 0 volts over there. Okay. And I also will write the circuit for t equal to 0 plus, that is just after the step is applied. So, there will be some voltage across C, some other voltage across C1, Vc1 of 0 plus, okay, and this value will be equal to Vp. Okay. So, now you see that in this case the charge on this plate is 0 and the charge on this plate in the second case is, what is the charge on this particular plate in the second case at t equal to 0 plus? It will be equal to Vc1 is defined with this polarity, right. So, let me just take a capacitor here. If I have a capacitor C with a certain voltage V across it, what it also means is that on this plate there is plus C times V charge and on this plate there is minus C times V. Okay. So, on this plate we have minus C times Vc1 of 0 plus. Okay. That is by the definition of a capacitor. When a capacitor C has a voltage V, there will be plus C times V on one plate, minus C times V on the other plate. It will be plus C times V on the plate with the positive sign of the voltage and minus C times V on the plate with negative sign of the voltage. Okay. So, the charge on this plate has changed from 0 to minus C Vc1 of 0 plus. Similarly, let me write down the charge on the other capacitor. The charge on this plate originally before the step will be 0 and just after the step will be C times Vc of 0 plus, that is plus C times Vc of 0 plus. Okay. So, now we can find these charges. The way I have written it is charge coming out of C1 has to be equal to charge going into C2. We can also write it in a conventional Kirchhoff's law formulation where the total charge leaving some node equals 0. Okay. Either way it is the same. In this case I will stick to the definitions I have written. So, what is the value of Q1? That is the amount of charge that is going from left to right in this wire just after the step. What will be the value of Q1 and what is the value of Q2? Q1 is what goes from here to there when it transitions from t equal to 0 minus to t equal to 0 plus. Okay. So, now the charge here was 0 and it changed to minus C Vc1 of 0 plus. So, obviously, a charge of plus C Vc1 0 plus has gone from left to right. Okay. What has gone this way is the negative of this quantity. So, Q1 equals C Vc1 of 0 plus, okay, and Q2, this Q2, which is the current flow, the charge flowing into the capacitor C, okay, this is not C2, that is C, equals C times Vc of 0 plus, because originally there was no charge on this plate, later there is a charge of C times Vc of 0 plus. So, Q2 is C times Vc of 0 plus. Okay. I think I wrote this wrongly. This capacitor C1. So, this is minus C1 Vc1 of 0 plus, and the charge on this plate, this capacitor is C times Vc of 0 plus. So, this is also C1, okay, not C. So, now C1 Vc1 of 0 plus equals C Vc of 0 plus. Okay. So, this comes from KCL, but reformulated in terms of charges. Okay. In addition to this, we also have the KVL, which has to be always satisfied, of course, okay, which says that Vc1 of 0 plus Vc of 0 plus, that is the sum of these two voltages, has to be equal to Vp. Okay. Now, from these two, you should be able to calculate both Vc1 just after the step is applied and Vc just after the step is applied. Okay. Please do that and let me know the value of Vc of 0 plus. Okay. So, as usual, we use KCL and KVL to determine everything, but in this case KCL is formulated in terms of charges, because the capacitor voltages are changing instantaneously and the currents are infinite, that is all. Okay. So, we have two equations, two unknowns, so we should be able to solve them. Okay, so please calculate Vc of 0 plus and let me know what it is. That is exactly right. So, when a step of Vp is applied to a capacitive divider, you see that this looks somewhat like a resistive divider, but with capacitors with C1 and C. The voltage here at t equal to 0 plus will change also instantaneously, and it changes from 0 to Vp times C1 by C plus C1. Okay. C1 is this capacitor and C is that capacitor. And you see that this formula is also reminiscent of the resistive divider formula, except that the roles are interchanged. Okay. In the case of resistors, you get R by R plus R1. Here you get C1 by C plus C1. Okay. And just to complete the picture, the voltage Vc1 will change from 0 to Vp times C by C plus C1. Okay. So, when you have a loop of voltage source and capacitors and you apply a step, the voltages of all capacitors in the loop will change abruptly. They have to. Okay. So, that I explained, and now you can also calculate how much they change by, and all you need to do is to write down KCL in terms of charges instead of currents. That is all. Okay. Any questions about this?